When astronauts return from spacewalks and remove their helmets inside the airlock, they consistently report something unexpected. Space has a smell. It's been described as a faint metallic odor, sometimes compared to hot metal or welding fumes. This isn't speculation or imagination. Multiple astronauts across different missions have independently reported this phenomenon. The smell doesn't come from space itself, but from residual particles and oxidized materials clinging to the suit's exterior that then interact with the air inside the station. It's a small detail, but it demonstrates something fundamental. Our experience of space, even through the barrier of technology, reveals properties we can measure and verify. Before we go further, if you're interested in understanding space through verified science and direct observation, consider subscribing and enabling notifications. This channel focuses exclusively on what we can demonstrate, measure, and confirm. Now, that metallic scent is just one of countless verified observations that reshape how we understand the universe beyond our atmosphere. Let's examine what we actually know, based on measurements, experiments, and physical laws that have been tested repeatedly. Space is often called a vacuum, and while that's directionally correct, it's not completely empty. Interstellar space contains radiation of various wavelengths, dust particles, and stray atoms, typically hydrogen. The density is extraordinarily low, perhaps 1 atom per cubic centimeter in some regions, but it's measurable. This matters because those particles, though sparse, affect how electromagnetic radiation propagates across cosmic distances. The average temperature of this space, measured by the kinetic energy of these particles, sits at approximately -270 degrees Celsius, just a few degrees above absolute zero. This has been confirmed through multiple measurement techniques, including observations of the cosmic microwave background radiation. That extreme cold interacts strangely with human biology. If an astronaut were suddenly exposed to vacuum without protection, one of the first physiological responses would be unexpected. Saliva would boil. Not because space is hot, but because boiling point depends on pressure. At the near-zero pressure of space, water transitions to vapor at body temperature. This has been demonstrated in vacuum chambers here on Earth. The human body contains water, and that water would begin vaporizing immediately. But contrary to some dramatic portrayals, the body wouldn't explode. Skin and tissue provide enough structural integrity to contain internal pressure for a brief period. What would happen more quickly is loss of consciousness. Depressurization causes oxygen in the lungs to be expelled, and without a fresh oxygen supply reaching the brain, unconsciousness occurs within about 15 seconds. Death would follow, but not from the lungs bursting as sometimes depicted. The actual cause would be oxygen deprivation and the cascade of physiological failures that follow. These conclusions come from documented accidents in vacuum chambers and high-altitude incidents, as well as controlled studies on the effects of rapid decompression. This brings us to one of space's most counterintuitive properties: silence. Sound requires a medium to propagate, molecules that can vibrate and transfer energy. In the near vacuum of space, there simply aren't enough particles to carry sound waves. Explosions, impacts, even the roar of a rocket engine produce no sound in space itself. We know this both from the physics of wave propagation and from direct observation during spacewalks. Astronauts cannot hear anything outside their suits except through radio transmission. The popular notion of noisy space battles is purely fiction. Yet despite this silence and emptiness, space is far from still. Time itself behaves differently depending on where you are and how fast you're moving. Satellites in orbit experience time at a slightly faster rate than clocks on Earth's surface. This isn't theoretical. It's been measured with atomic clocks and must be corrected for systems like GPS to function accurately. The effect comes from two aspects of relativity: gravitational time dilation, where time passes more slowly in stronger gravitational fields, and velocity-based time dilation from the satellite's orbital speed. The gravitational effect dominates for GPS satellites, causing their clocks to run faster by about 45 microseconds per day compared to Earth-based clocks. Without correcting for this, GPS positioning would drift by kilometers within a single day. The human body itself changes in profound ways when removed from Earth's gravity. Astronauts consistently grow taller in microgravity, typically by several centimeters. This occurs because the spine, no longer compressed by body weight, extends. The effect is temporary and reverses upon return to Earth, but it's been documented on every long-duration space mission. Fluid distribution also changes dramatically. On Earth, gravity pulls blood and other fluids toward the lower body. In orbit, this pull disappears, and fluids shift toward the head and upper body. Astronauts often report a feeling of fullness in the head, and their faces appear puffy in photographs taken aboard the International Space Station. The heart responds to this redistribution by changing shape. On Earth, gravity influences the heart's orientation and the distribution of blood within its chambers. In microgravity, the heart becomes more spherical, a change that's been documented through ultrasound imaging aboard the ISS. This isn't harmful in the short term, but it represents a fundamental restructuring of cardiovascular function that raises questions about long-duration missions. Speaking of the ISS, it's one of the brightest artificial objects in the night sky. The station orbits at an altitude of roughly 400 kilometers and reflects sunlight efficiently due to its large solar arrays. On a clear night, when the station passes overhead during the right lighting conditions, typically shortly after sunset or before sunrise, it's visible to the naked eye as a bright point moving steadily across the sky. This has been observed and photographed by millions of people worldwide. No telescope is required, just knowledge of when to look. The existence of the ISS and other satellites creates a growing problem: orbital debris. Objects in low Earth orbit travel at approximately 7 to 8 kilometers per second to maintain their altitude. At these velocities, even tiny fragments, paint flecks, metal shards from deteriorating spacecraft, carry enormous kinetic energy. A particle just 1 centimeter across moving at orbital velocity hits with the force of a hand grenade. This has been demonstrated both through impact modeling and actual damage to spacecraft, including cracked windows on the Space Shuttle and impact marks on the ISS. This debris remains in orbit because there's no atmospheric drag to slow it down at those altitudes. Objects can circle Earth for decades or centuries before their orbits decay enough to re-enter the atmosphere. The problem is cumulative. Collisions create more debris, which increases the probability of further collisions, a scenario known as the Kessler syndrome. But let's step away from human-made objects and consider natural phenomena. Fire, for instance, behaves strangely in microgravity. On Earth, hot gases rise due to buoyancy, creating the familiar teardrop shape of a flame. Without gravity to create buoyancy-driven convection, flames in space form spheres. This has been observed in numerous combustion experiments aboard the ISS. The flame burns in a roughly spherical shell around the fuel source, fed by oxygen diffusion rather than convective flow. Understanding this matters for fire safety on spacecraft and for developing more efficient combustion processes. Even tears behave differently. On Earth, tears flow down the face due to gravity. In microgravity, surface tension dominates, and tears accumulate into small spherical bubbles that cling to the eye or face. Astronauts have reported this phenomenon, noting that crying in space requires wiping the tears away manually since they won't fall naturally. Beyond Earth orbit, the properties of celestial objects become even more extreme. Neutron stars represent matter compressed to densities that exceed even atomic nuclei. A neutron star with a mass roughly 1.4 times that of the Sun might have a diameter of only about 20 kilometers. A single teaspoon of neutron star material would have a mass of roughly 1 billion tons. These measurements come from observations of neutron star masses through binary systems and their rotation rates through pulsar timing. Some neutron stars, particularly millisecond pulsars, rotate at extraordinary rates, hundreds of complete rotations per second. The fastest confirmed pulsar, PSR J1748-2446 AD, rotates 716 times per second. At this rate, the star's surface is moving at a significant fraction of the speed of light, yet the star's immense gravity and structural integrity from neutron degeneracy pressure keep it from flying apart. We know these rotation rates with precision because pulsars emit beams of radiation that sweep across Earth like a lighthouse, and we can measure the interval between pulses with extreme accuracy. Closer to home, within our own solar system, planetary properties reveal equally surprising physics. Venus rotates so slowly that its day, one complete rotation on its axis, is longer than its year, the time it takes to orbit the Sun. A Venusian day lasts about 243 Earth days, while its year is about 225 Earth days. Additionally, Venus rotates in the opposite direction to most planets, a phenomenon called retrograde rotation. These measurements come from radar mapping and observations of Venus's cloud movements. Mercury, the closest planet to the Sun, experiences temperature variations more extreme than any other planet in our solar system. Daytime temperatures on the Sun-facing side can exceed 400 degrees Celsius, while nighttime temperatures on the dark side plummet to minus 180 degrees Celsius. This range of nearly 600 degrees occurs because Mercury has almost no atmosphere to distribute heat, and its rotation is slow compared to its orbit, leaving each hemisphere exposed to either continuous sunlight or continuous darkness for extended periods. Moving outward, Jupiter's immense gravitational field dominates the orbital dynamics of the inner solar system. The planet's gravity alters asteroid trajectories, sometimes capturing objects into temporary orbits, sometimes ejecting them from the solar system entirely, and sometimes redirecting them toward the inner planets. This gravitational influence has shaped the structure of the asteroid belt and affects the distribution of comets. Computational models and direct observation of asteroid orbits confirm Jupiter's role as a gravitational shepherd. Saturn, despite being a gas giant with tremendous mass, has an average density lower than water. If you could find an ocean large enough, Saturn would theoretically float. This is because the planet is composed primarily of hydrogen and helium, light elements that exist as gases or low-density fluids under the temperature and pressure conditions in Saturn's outer layers. The planet's average density has been calculated from its mass, determined by its gravitational effects on its moons, and its volume, measured from direct observation. Uranus presents another rotational oddity. It rotates on its side, with its rotational axis tilted approximately 98 degrees from the perpendicular to its orbital plane. This means the planet essentially rolls around the Sun rather than spinning like a top. The cause of this extreme tilt remains uncertain, but it's been proposed that a massive collision early in the solar system's history could have knocked the planet onto its side. What we can verify is the tilt itself, confirmed through observations of the planet's magnetic field orientation and the motion of its moons. Mars hosts geological features that dwarf Earth's. Olympus Mons, the largest volcano in the solar system, rises approximately 21 kilometers above the Martian reference level, more than twice the height of Earth's tallest mountain, Mauna Kea, when measured from its base on the ocean floor. The volcano's base spans roughly 600 kilometers. These dimensions have been measured through orbital mapping and altimetry data from multiple Mars missions. The volcano's size is possible partly because Mars lacks plate tectonics, allowing volcanic activity to build upward in one location over geological timescales without the crust shifting. Mars also shows extensive evidence of ancient liquid water. Orbital imaging reveals valley networks, dried lake beds, and mineral deposits that form only in the presence of water. Rover missions have analyzed rocks and sediments that formed in aqueous environments. The evidence is multifaceted: morphological features like channels and deltas, mineralogy including hydrated salts and clays, and sedimentary structures consistent with water deposition. This doesn't confirm life existed on Mars, but it establishes that conditions suitable for liquid water were present billions of years ago. Now let's turn to objects even more extreme than neutron stars: black holes. These are regions where space-time curvature becomes so extreme that not even light can escape once it crosses the boundary called the event horizon. This isn't speculation, it follows directly from general relativity, and the existence of black holes has been confirmed through multiple independent observations. The orbital motion of stars around invisible massive objects, gravitational wave detection from black hole mergers, and even direct imaging of the shadow of a black hole in the galaxy M87. Near a black hole's event horizon, time dilation becomes extreme. To a distant observer, time appears to slow down for anything approaching the horizon, eventually appearing to freeze at the boundary. This effect has been calculated using general relativity and is consistent with observations of matter falling toward black holes. Nothing that crosses the event horizon can return, because escape would require exceeding the speed of light, which is physically impossible. Interestingly, black holes are not permanent. Stephen Hawking demonstrated theoretically that black holes emit radiation due to quantum effects near the event horizon, a process now called Hawking radiation. This radiation causes black holes to lose mass extremely slowly, eventually evaporating completely. For a black hole with the mass of the Sun, this evaporation would take roughly 10 to the 67th power years, incomprehensibly longer than the current age of the universe. While Hawking radiation has not been directly observed due to its faintness, it follows from well-established principles of quantum mechanics and general relativity. On galactic scales, structures and motions unfold over timescales far exceeding human comprehension. The Milky Way, our home galaxy, is on a collision course with the Andromeda Galaxy. The two galaxies are approaching each other at roughly 110 kilometers per second and will merge in approximately 4 to 5 billion years. This timeline is derived from measurements of Andromeda's motion using Doppler shifts of its light and proper motion measurements from observations spanning decades. When galaxies collide, they can pass through each other without most stars directly colliding. This seems paradoxical until you consider the scale. Stars are separated by vast distances relative to their sizes. Even though a galaxy contains hundreds of billions of stars, the volume of space is so immense that the probability of two stars physically impacting during a galactic merger is extremely low. What does happen is gravitational disruption, which reshapes both galaxies and can trigger bursts of new star formation as gas clouds collide and compress. The composition of the universe itself is dominated by components we cannot directly see. Observations of galaxy rotation curves, gravitational lensing, and the large-scale structure of the universe indicate that normal matter, the atoms and molecules that make up stars, planets, and everything we can observe directly, accounts for only about 5% of the universe's total mass energy content. Approximately 27% is dark matter, a form of matter that doesn't emit or absorb light but exerts gravitational effects. About 68% is dark energy, an even more mysterious component associated with the accelerating expansion of space itself. These percentages come from multiple independent measurements, including the cosmic microwave background radiation, the distribution of galaxies across cosmic distances, and observations of distant supernovae. The evidence is robust, even though the fundamental nature of dark matter and dark energy remains unknown. The universe has no confirmed center. This is a consequence of cosmological observations showing that space is expanding uniformly in all directions. From any vantage point, distant galaxies appear to be receding, with velocity proportional to distance, a relationship called Hubble's law. This expansion isn't objects moving through space, but space itself expanding. There's no special location from which this expansion emanates, no center point. Every location sees the same pattern of expansion. Moreover, this expansion is accelerating. Observations of Type I supernovae, which serve as standard candles for measuring cosmic distances, reveal that the expansion rate of the universe is increasing over time. This discovery, made in the late 1990s, led to the concept of dark energy as a driving force. The acceleration has been confirmed through multiple independent observation methods. Beyond our solar system, exoplanets exhibit properties that stretch our understanding of planetary physics. Some gas-giant exoplanets orbit extremely close to their host stars, experiencing temperatures exceeding 2,000 degrees Celsius, hot enough to vaporize metals and create atmospheric conditions more extreme than the surface of molten lava. These hot Jupiters have been detected through transit photometry and radial velocity measurements, and their temperatures can be estimated from their distance from the star and the star's luminosity. On some of these extreme planets, atmospheric pressure and temperature conditions may create precipitation of solid carbon, essentially diamond rain. This is not confirmed through direct observation but follows from thermodynamic models of carbon chemistry under the extreme conditions present in these atmospheres. Laboratory experiments recreating similar pressures and temperatures support the possibility. Many exoplanets lack solid surfaces entirely. Gas giants like Jupiter have atmospheres that gradually increase in density and pressure with depth, transitioning smoothly from gas to liquid to exotic high-pressure states. But there's no distinct solid surface to stand on. This has been inferred from our understanding of planetary formation, confirmed observations of Jupiter, and models of exoplanets with similar composition. Not all planets orbit stars. Rogue planets drift through interstellar space, unbound to any stellar system. These objects likely formed in planetary systems, but were gravitationally ejected through interactions with other planets or passing stars. Detecting rogue planets is challenging because they emit no light of their own and reflect no starlight, but some have been found through gravitational microlensing, where the planet's gravity briefly magnifies the light of a more distant star. Stars themselves end in various ways depending on their mass. Massive stars conclude their lives in supernovae, explosions so luminous they can temporarily outshine entire galaxies. A single supernova can briefly emit as much energy as the Sun will radiate over its entire 10 billion year lifetime. These events have been observed throughout history, with modern detections occurring regularly in distant galaxies. Supernovae serve a crucial function in cosmic chemistry. They forge heavy elements. The intense temperatures and neutron flux during the explosion create elements heavier than iron through rapid neutron capture. These elements are then dispersed into space, enriching the interstellar medium and providing the raw material for new generations of stars and planets. The evidence for this is found in the correlation between supernova remnants and enhanced abundances of heavy elements, as well as in the detailed nuclear physics of nucleosynthesis. For humans attempting long-duration space travel, the environment poses severe biological challenges. In microgravity, bone density decreases rapidly, particularly in weight-bearing bones like the hips and spine. Astronauts can lose 1 to 2% of bone mass per month during spaceflight. This has been measured through bone density scans before and after missions. The loss occurs because bones adapt to mechanical loading. Without the constant stress of gravity, the body reduces bone mass to save resources. Muscle atrophy follows a similar pattern, accelerating in the absence of gravitational resistance. Even with rigorous daily exercise, astronauts lose muscle mass and strength during long missions. Muscle loss can reach 20% for some muscle groups over 6 months in space. This has been documented through physical measurements and biopsy studies of astronauts on the ISS. Vision changes represent another concern for long missions. Many astronauts experience changes in eye structure, including flattening of the eyeball and swelling of the optic nerve. These changes, collectively called spaceflight-associated neuroocular syndrome, are thought to result from the fluid shift toward the head in microgravity, which increases intracranial pressure. Some vision changes persist after return to Earth, confirmed through eye examinations and imaging studies. Radiation exposure in space poses long-term health risks. Beyond Earth's protective magnetosphere and atmosphere, astronauts are exposed to cosmic rays and solar radiation at levels far exceeding anything experienced on Earth's surface. This radiation damages DNA, increasing cancer risk and potentially affecting other organ systems. The dose rates have been measured with radiation detectors aboard spacecraft, and the biological effects are extrapolated from studies of radiation exposure in medical and occupational contexts. Even Earth's relationship with its moon involves gradual change. The moon is drifting away from Earth at a rate of about 3.8 centimeters per year. This occurs because tidal interactions transfer angular momentum from Earth's rotation to the moon's orbit. The rate has been measured with extraordinary precision using laser ranging, where laser pulses are bounced off reflectors placed on the moon's surface by Apollo astronauts. The time for the light to return allows calculation of the Earth-Moon distance to within millimeters. As the moon drifts away, Earth's rotation slows. The same tidal forces that push the moon outward exert a braking effect on Earth's rotation. Days are getting longer by about 1.7 milliseconds per century. This may seem negligible, but over geological time, it's significant. Evidence for slower rotation in the past comes from growth patterns in ancient coral fossils, which show daily and yearly cycles. These fossils indicate that hundreds of millions of years ago, days were shorter and there were more days in a year. Returning to human spaceflight, the cost and complexity of equipment is substantial. A single spacesuit used for extravehicular activity costs over $10 million. This figure, reported by NASA, reflects the suit's sophisticated life support systems, radiation shielding, thermal regulation, and the extensive testing required to certify it for use in vacuum. The suit is essentially a miniature spacecraft, providing oxygen, removing carbon dioxide, regulating temperature, and protecting against micrometeorite impacts. Daily life aboard a space station requires constant adaptation to microgravity. Astronauts must strap themselves into sleeping bags anchored to walls, as there is no down in orbit and they would otherwise drift around the cabin. This sleeping arrangement has been standard practice since the earliest space stations. The Sun, our nearest star, constantly loses mass through two processes: the solar wind, a stream of charged particles flowing outward from the sun's corona, and the conversion of mass to energy through nuclear fusion in its core. The total mass loss is approximately 4 million tons per second. Despite this enormous rate, the sun is so massive that this loss is negligible over human timescales. The mass loss rate has been calculated from measurements of the solar wind and from the energy output of the sun combined with Einstein's mass-energy relation. Light from the sun takes approximately 8 minutes to reach Earth. This is calculated directly from the speed of light and the Earth-sun distance. It means we always see the sun as it was 8 minutes ago. If the sun suddenly vanished, Earth would continue receiving light and heat for 8 minutes before experiencing any change. The sun is approximately halfway through its main sequence lifetime. In about 5 billion years, as hydrogen fuel in its core depletes, the sun will expand into a red giant, swelling to a size that may engulf Earth's orbit. Before this occurs, though, Earth will become uninhabitable. As the sun ages and its fusion processes evolve, its luminosity will gradually increase. Within roughly 1 billion years, this increased luminosity will heat Earth enough to evaporate the oceans and create a runaway greenhouse effect, sterilizing the planet long before the sun's red giant phase. Interstellar space, while mostly empty, contains trace amounts of organic molecules. Spectroscopic observations have identified over 200 different molecules in interstellar clouds, including complex organic compounds like amino acids and even ethanol. These molecules form through chemical reactions in cold molecular clouds and have been detected through their absorption and emission signatures at specific wavelengths. The presence of alcohol molecules in space, particularly in vast clouds near star-forming regions, has been confirmed through radio telescope observations. Water, essential for life as we know it, exists in various forms throughout the solar system. The Moon, long thought to be completely dry, contains water ice in permanently shadowed craters near its poles. This has been confirmed through neutron spectroscopy, infrared spectroscopy, and direct observation by instruments aboard lunar orbiters. Water vapor has been detected in the atmospheres of several exoplanets through transit spectroscopy, where starlight passing through the planet's atmosphere reveals absorption signatures of water molecules. Several moons in our solar system contain subsurface oceans beneath their icy crusts. Europa, a moon of Jupiter, likely harbors a global ocean of liquid water beneath a shell of ice. Evidence includes surface features consistent with ice floating on liquid, magnetic field measurements suggesting a conductive layer beneath the surface, and plumes of water vapor observed erupting from the surface. Europa may contain more liquid water than all of Earth's oceans combined, a conclusion based on estimates of the Moon's ice shell thickness and internal structure derived from gravitational measurements. The fundamental structure of space itself is curved by the presence of mass and energy. This is the central insight of general relativity. Gravity is not a force in the traditional sense, but rather the curvature of spacetime. Mass tells spacetime how to curve, and curved spacetime tells mass how to move. This has been confirmed through numerous observations, including the precise motion of Mercury's orbit, gravitational lensing of distant galaxies, and the detection of gravitational waves. Light itself bends when passing near massive objects, following the curved geometry of spacetime. This gravitational lensing has been observed countless times, from the bending of starlight during solar eclipses to the multiple images and arcs of distant galaxies seen around massive galaxy clusters. The amount of bending depends on the mass of the lensing object and its distance, matching theoretical predictions precisely. When we look into space, we're looking into the past. Light has a finite speed, so the image we see of a distant object shows that object as it was when the light began its journey. The nearest star beyond the Sun, Proxima Centauri, is 4.24 light-years away, meaning we see it as it was 4.24 years ago. For distant galaxies billions of light-years away, we observe them as they existed billions of years ago, when the universe was much younger. The universe is permeated by cosmic microwave background radiation, the remnant heat from the Big Bang. This radiation, discovered in 1964, has a nearly uniform temperature of about 2.7 Kelvin and fills all of space. Its spectrum matches a thermal blackbody almost perfectly, and tiny variations in its temperature across the sky provide information about the density fluctuations in the early universe that eventually grew into the galaxies and large-scale structures we observe today. From this radiation and other measurements, cosmologists have determined that the universe is approximately 13.8 billion years old. This age comes from multiple independent methods: the expansion rate of the universe, the oldest observed star clusters, radioactive dating of the oldest Earth rocks and meteorites, and detailed analysis of the cosmic microwave background. All methods converge on an age near 13.8 billion years. Earth's history includes at least 5 major mass extinction events, identified through dramatic changes in the fossil record. The most severe, the Permian-Triassic extinction about 252 million years ago, eliminated roughly 90% of marine species and 70% of terrestrial vertebrates. The most recent, the Cretaceous-Paleogene extinction 66 million years ago, killed the non-avian dinosaurs and many other species. The cause of this event has been traced to an asteroid impact, evidenced by a global layer of iridium-rich sediment, shocked quartz, and the Chicxulub crater in Mexico. Some meteorites found on Earth originated from Mars. This has been confirmed through analysis of gases trapped within the meteorites, which match the Martian atmospheric composition measured by landers on Mars. These meteorites were ejected from Mars by powerful impacts and eventually fell to Earth. Their study provides direct samples of Martian rock without the need for a sample return mission. Asteroids contain significant quantities of valuable metals, including platinum group metals, iron, and nickel. Spectroscopic analysis of asteroid composition and study of meteorites, which are fragments of asteroids, reveal these abundances. Some asteroids are essentially solid metal, remnants of the cores of larger bodies that were disrupted by collisions early in the solar system's history. Mining these resources is physically possible, though economically and technically challenging with current technology. The fundamental physics of extracting and transporting materials from asteroids is well understood, and mission concepts have been developed in detail. Whether and when asteroid mining becomes practical depends on technological development and economic factors, not on physical impossibility. The brain adapts rapidly to microgravity. Astronauts experience spatial disorientation initially, as the vestibular system, which senses gravity and acceleration, receives conflicting signals. However, within a few days, most astronauts adapt and regain functional spatial awareness. This neuroplasticity has been demonstrated through balance tests and functional imaging studies before and after spaceflight. Taste and smell are dulled in space. The fluid shift toward the head creates a sensation similar to having a stuffy nose, which diminishes the sense of smell. Since smell is crucial for flavor perception, food tastes blander to astronauts. This has been reported consistently across missions, and astronauts often request spicier or more strongly flavored foods. Plants grow differently without gravity's directional cue. On Earth, roots grow downward and shoots grow upward in response to gravity, a process called gravitropism. In microgravity, plants use other cues, including light direction and moisture gradients, but their growth patterns differ from Earth-grown plants. Experiments aboard the ISS have documented these differences, showing altered root architecture and changes in gene expression related to growth regulation. Human reproduction in space remains uncertain. No human has conceived, gestated, or been born in space, so direct evidence is lacking. Animal studies have shown that conception and early development can occur in microgravity, but with higher rates of developmental abnormalities. The effects of radiation, altered gravity, and other space environment factors on human reproduction are areas of active research, but comprehensive answers require data we don't yet have. When viewed from space, Earth appears remarkably smooth. At the planetary scale, even the tallest mountains are negligible features. Mount Everest, at 8.8 kilometers above sea level, represents a deviation of only about 0.14% from Earth's average radius of 6,371 kilometers. The planet's equatorial bulge, caused by rotation, is a larger deviation from perfect sphericity than any mountain. Astronauts consistently describe Earth as appearing smooth when viewed from orbit. Some stars visible in the night sky are already dead. Light from these stars has traveled for years, decades, or even centuries to reach us. If a star 500 light-years away died today, we wouldn't see it disappear for 500 years. However, most naked-eye stars are relatively nearby in cosmic terms, within a few hundred light-years. And for stars like the Sun, which live for billions of years, the probability that any particular visible star has died since emitting the light we see is actually quite low. The Moon is tidally locked to Earth, always showing the same face to us. This occurred because Earth's tidal forces on the Moon slowed the Moon's rotation until its rotational period matched its orbital period. The synchronization is stable and has persisted for billions of years. The far side of the Moon, often incorrectly called the dark side, receives just as much sunlight as the near side but was completely unknown until spacecraft photographed it in 1959. Astronauts aboard the ISS don't float because there's no gravity. They float because they're in continuous free fall. The station is falling around Earth in a stable orbit. Gravity at the ISS's altitude is only about 10% weaker than at Earth's surface. The sensation of weightlessness comes from the fact that the station, the astronauts, and everything inside are all falling together at the same rate. There's no contact force from a floor or seat, hence the sensation of floating. The Sun is a star, a fact so familiar it's easy to forget its significance. It's not a special category of object, but an ordinary main-sequence star, one of hundreds of billions in the Milky Way galaxy alone. What makes it unique to us is proximity. It's close enough to provide the light and heat necessary for life on Earth, and close enough to study in detail that's impossible for other stars. Space is extremely cold in the absence of direct sunlight, with temperatures approaching the background temperature of the universe at about 2.7 Kelvin. However, objects in sunlight can become very hot, as there's no atmosphere to convect heat away. This is why spacecraft require thermal control systems to balance heating from the sun with radiative cooling to space. There is no breathable oxygen in space. The near vacuum contains only trace atoms and molecules, far too sparse to support respiration. Humans require oxygen at a partial pressure similar to sea level on Earth, delivered continuously. Space suits and spacecraft provide this through stored oxygen or oxygen generation systems. Earth orbits the Sun at an average distance of about 150 million kilometers, completing one orbit in approximately 365.25 days. This orbital motion results from the balance between Earth's velocity and the Sun's gravitational pull. If Earth moved faster, it would escape to a higher orbit. If slower, it would spiral inward. Gravity exists everywhere in the universe. It's not something that can be turned off or escaped. Even in the depths of intergalactic space, far from any massive object, gravity from distant galaxies exerts a force, though immeasurably small. What we call microgravity aboard spacecraft is not the absence of gravity, but a state of continuous free fall where gravitational force is balanced by orbital motion. 12 humans have walked on the Moon between 1969 and 1972 during the Apollo program. They conducted experiments, collected samples, and left instruments that continued to provide data. The evidence for these landings is overwhelming: hundreds of kilograms of lunar samples, photographs and video, laser reflectors still used for precise Earth-Moon distance measurements, and independent verification by spacecraft from multiple nations that have photographed the landing sites. Thousands of satellites orbit Earth continuously, serving purposes from communication and navigation to Earth observation and scientific research. These satellites remain in orbit because their velocity perpendicular to Earth's gravitational pull keeps them falling around the planet rather than falling into it. The orbital velocity required depends on altitude, with lower orbits requiring higher speeds. The Milky Way galaxy contains between 100 and 400 billion stars, though the exact number is uncertain because large portions of the galaxy are obscured by dust. This estimate comes from star counts in visible regions, models of galactic structure, and the total mass and luminosity of the galaxy. Each star is potentially surrounded by planets, meaning the number of worlds in our galaxy alone is staggering. Space appears dark despite containing countless stars because of the inverse square law of light and the vast distances involved. Light spreads out as it travels, diminishing in brightness with the square of the distance. Even though there are billions of galaxies, each containing billions of stars, most are so distant that their light is too faint to contribute noticeably to the overall brightness of the sky. This is known as Olber's paradox, and the explanation involves both the finite age of the universe and cosmic expansion. Light travels at 299,792 kilometers per second in vacuum, a speed that has been measured with extraordinary precision. This speed is not just very fast, it's a fundamental constant of nature. Nothing with mass can reach or exceed this speed, a consequence of special relativity. The constancy of light's speed regardless of the observer's motion leads to time dilation, length contraction, and mass-energy equivalence. Black holes do not indiscriminately suck everything nearby. They have gravity like any other object, and their gravitational pull at a given distance depends only on their mass. If the Sun were suddenly replaced by a black hole of equal mass, Earth's orbit would remain unchanged. Black holes only dominate their immediate vicinity, where space-time curvature becomes extreme. The Moon affects Earth's tides through gravitational force. The Moon's gravity pulls on Earth's oceans, creating bulges of water on the side facing the Moon and, less intuitively, on the opposite side as well. As Earth rotates, these bulges remain roughly aligned with the Moon, resulting in 2 high tides and 2 low tides each day at most coastal locations. The Sun also contributes to tides, and when the Sun and Moon align, their effects combine to create higher spring tides. Space is silent, as we established earlier, because sound requires a medium to propagate. This property makes spacewalks eerily quiet experiences. Astronauts hear only sounds transmitted through their suit's structure or through radio communication, never anything from the environment outside. Earth is tiny relative to the universe. The observable universe extends roughly 46 billion light-years in every direction from Earth, a sphere containing an estimated 2 trillion galaxies. Earth, with a diameter of about 12,700 kilometers, is incomprehensibly small by comparison. The ratio is beyond human intuition, like comparing a single atom to a planet. Humanity has explored only a minuscule fraction of space. All human spaceflight has been confined to near-Earth orbit except for the Apollo missions to the Moon, which traveled a maximum distance of about 400,000 kilometers from Earth. The nearest star beyond the Sun is 10,000 times farther away. The Voyager spacecraft, launched in 1977 and now in interstellar space, have traveled less than 1/5 of a light day from Earth after more than 4 decades. At Voyager's speed, reaching even the nearest star would take tens of thousands of years. Every fact presented in this discussion derives from observation, measurement, and experimental verification. Science proceeds by testing predictions, gathering data, and building models that match what we can detect and measure. The universe reveals its properties through phenomena we can document: electromagnetic radiation across all wavelengths, gravitational effects on visible matter, particle physics verified in accelerators, and direct exploration where technology permits. What we've covered represents a foundation of verified knowledge about space, from the immediate environment around Earth to the large-scale structure of the cosmos. Each fact connects to evidence: telescope observations, spacecraft measurements, laboratory experiments, or mathematical frameworks tested against reality. The universe is far stranger than everyday experience suggests, but it's comprehensible through systematic investigation. Understanding space requires accepting that human intuition, developed in Earth's gravity with atmospheric pressure and moderate temperatures, often misleads us. Space operates by the same physical laws, but the conditions are so different that outcomes surprise us. Flames form spheres. Time runs at different rates. Dense objects curve space itself. Yet all of this becomes logical when we understand the underlying principles. As exploration continues and technology advances, we'll refine measurements, discover new phenomena, and occasionally revise our models. But the foundation of what we know, verified through multiple independent methods and tested extensively, provides a reliable framework for understanding our place in the cosmos. If this approach to space science interests you, consider subscribing to stay updated with future content. This channel will continue to focus on what we can demonstrate and verify, presenting space as it reveals itself through observation rather than speculation. The universe is vast, ancient, complex, and fundamentally knowable through patient investigation. That combination makes it endlessly fascinating to explore.